So I'd like to thank the Blue Waters team for inviting me to come and give this talk. It's an honor and a privilege, and I really appreciate the opportunity. The Blue Waters Project has been an important part of my career. I actually started at Michigan State University shortly after submitting my first PRAC grant, and I have been running on this machine pretty much since I started my job at Michigan State, and it's really shaped the way that my career has gone. Okay, so my charge for today was to review the impact of Blue Waters on astronomical and space sciences over the past 5 years. So basically, everything from the top of the Earth's atmosphere to the edge of the universe in 30 minutes with leaving time for questions. So no big deal, we'll do that. As I was looking through all of the Blue Waters annual reports and all of the information people gave me, I realized it would be just completely impossible to talk about all the amazing science that's been done on Blue Waters, so I am going to address some of the highlights. Apologize to those whose work I don't mention. If you're unhappy about that, please direct your complaints to Bill Kramer, who would be delighted to hear them. Okay, so that's right. So I'd like to address a few questions during this talk. First, I would like to talk about why the fields of astronomy and astrophysics and space science desperately need large-scale and high-performance computing in order to make any progress whatsoever. I also want to address the issue of why Blue Waters is particularly awesome for scientific challenges in this area. And finally, and perhaps most importantly, I'm going to talk about the science that's been done on Blue Waters in these fields. But before that, I'd like to thank a bunch of people. I emailed all of my colleagues whose names I was given by NCSA, and I am really overwhelmed by the quantity of responses and also the quality. Some of you sent me gigabytes of information. I wish you had not emailed it, but it was still useful. But the outpouring of information and visualizations was really very helpful. I also want to thank Bill and the rest of the Blue Waters team for their hard work and dedication. In particular, I really want to thank the system administrators and the user support and the technical points of contact. I've worked on a lot of supercomputers in my career, and Blue Waters has been my favorite one to run on because of all of the support that's been given to us by the people there. And it's very clear that everyone who's involved is really excited about supporting the science that's going on the machine, and that makes a tremendous difference to me as a user, and I really appreciate it. And of course, you know, the people who give us money for all sorts of things, including the NSF. All right, so let's get with it. So why do we need high-performance computing in astronomy, astrophysics, and the space sciences? There's a few reasons. So one of them is that we're dealing with things that almost by definition you can't do on Earth. There are ways to take some astrophysical phenomena and scale them down so that you can do laboratory experiments. But most of the phenomena that we care about in the universe, outside of the Earth's atmosphere, and we'll go into detail in a minute, are physically complicated. There's lots of different types of physics going on simultaneously over very large dynamic ranges in space and time. And a lot of the time you can't exploit symmetries. You can't assume everything is a spherical cow or a spherical star. And so, in other words, you can only really explore these problems with large-scale computing and very carefully thought out algorithms and codes. Also, sometimes you simply have to deal with huge numbers of objects, whether those are stars or galaxies. And one of the reasons for that is, you know, there's a whole universe of weird phenomena out there, and sometimes you need to simulate large populations of those objects to find the rare ones to learn something really crucial about the universe. Okay, so how has Blue Waters contributed to these endeavors over the last 5 years? So first off, the hardware is really well suited to this. There are lots of computing cores, so that helps speed up the time to solution. It also has a lot of memory per node. Many of the problems that we deal with have tons of physics, as I said, and also when we want to do large populations, we're really relying on the ability to weak scale out to basically as much as we can fit in memory on the computer. And there are many problems, a couple that I'll highlight here, where fundamentally the biggest problem, you know, we want to do the biggest problem that we can jam into RAM on that computer. Also, Blue Waters has a great interconnect. It's high bandwidth and low latency, and a lot of the applications that I'm going to talk about have a lot of communication. And finally, and this is something that most people skimp on when they're buying a supercomputer, the file system is both very fast and very large. And both of these things are important because the kinds of simulations that we deal with typically generate vast volumes of data, and you need to write that data to something really quickly, and then you need to read it back in really quickly to analyze it and visualize it, and so on. And so when I've been sitting down with some of the other PIs talking about this, and so we've all generated petabytes of data on this machine, much to the dismay of the people who have to store it. Okay, so one of the other ways that Blue Waters has contributed has been fundamentally computing time. Almost precisely 25% of the allocated Blue Waters time has gone to astronomical and space science applications. And so, as the saying goes, quantity has a quality all its own. Huge simulations are necessary for advances in these fields, and that's one of the most important things here. It's an enormous resource. About 210 million node hours have gone to the astronomical and space sciences. So the Blue Waters staff were kind enough to share some information about power consumption for Blue Waters, and so you guys might remember that SpaceX launched a Tesla Roadster fairly recently into space for publicity reasons. I did the work, I did the math, and so to do all of the astronomical and space sciences calculations on Blue Waters took about 0.4 petajoules of energy. That's 0.4 times 10 to the 15, which seems appropriate for a petascale computer. As a side note, that is enough energy to send a Tesla Roadster not to Mars, but out of the galaxy. We could send that Roadster to Andromeda if you were willing to wait long enough. So I encourage the physicists in the audience to check my math. 0.4 times 10 to the 15 joules. And a Roadster weighs 1,200 kilograms. Go to it. And then the other thing that I think is really important, and something that I have been really impressed by, is all of the educational and outreach programs that have been done with Blue Waters. And there's a list of them right here, but this is unique to the Blue Waters project as far as I know, and it's incredibly important for both keeping the public aware of and supporting what we're doing with these very expensive, very complicated machines, and also training the next generation of computational and data scientists. And a lot of students of mine and my collaborators have taken advantage of many of these opportunities, and I really hope that this continues in the future with Blue Waters' successor. Okay, so now onto the science. To some extent, what I could do is just sit here and just show pretty picture after pretty picture. That is what I'm going to do, by the way. But I'm also going to work in some of the science. And as I said before, it's really difficult to mention everybody who has done really wonderful work on Blue Waters, or even a tenth of the information that people shared with me. And so I apologize for anything that I have omitted. Every bullet point that I'm going to show is an hour-long talk in its own right, if not a dissertation or a big chunk of someone's career. And so I was trying to think about how to organize this talk, and I decided that I'm going to start at the solar system and just work my way outwards. As a side note, that is roughly going to go in order of my increasing knowledge of the subject. So again, apologies if I say something wrong. Direct complaints to Bill. And also, as a side note, I'm not going to put up paper citations because that's just an awful lot of text. I'm just going to put up the PIs of the allocations. If you're interested in finding a paper relating to something, a lot of this is in the Blue Waters annual report, and the rest I'd be happy to send you. So, all right, buckle up, folks. So, first off, I'm going to talk about Earth and the solar system. And again, just highlighting some of the cool results. Thank you. So one of the most interesting results that I've seen is this work that I think Matt Clement did, which is modeling the formation of the terrestrial planets. And so this is a really cool project that was done on Blue Waters, and it's a simulation of how planetesimals in the early solar system grow and fragment. And so fundamentally, solar systems, it's hard to understand, it's hard to model how our own solar system formed and how you got the terrestrial planets on the inside and the gas giants on the outside, and precisely how that happens. And so simple models of the formation of the solar system have failed to reproduce our solar system for a long time. And Clement's work is one of the first ones that managed to do this, and so to get a good model of how the terrestrial planets formed by starting out with very small planetesimals, which I think this is going to keep looping, how the planetesimals both merged together and occasionally fragmented, and how the gas giants, which are those big black circles on the outside, affected, by gravitational tidal forces, all of these things going on in the inner solar system. And they needed blue waters because you need to do lots of these simulations, and also the GPU acceleration of all the gravitational force calculations is very helpful. The other planetary science or exoplanet result that I saw this week was by Ethan Cruz, who was showing how blue waters has been used to analyze data from the sort of second life of the Kepler planet finding satellite, and the preliminary work there to find new exoplanets was really amazing. And he's going to, Blue Waters or its successor is undoubtedly going to be used for TESS, the next planet finding mission, to analyze that data. Okay, so the next thing I want to talk about is space weather. So space weather basically means wind from the sun. So the sun is, a ball of gas. Technically, it's a ball of incandescent plasma, and it tends to, it has a solar wind of hot charged particles and magnetic fields that come out from it, and cosmic rays and all sorts of things like that. And so the Earth itself has a magnetosphere, so the Earth has a dynamo, and as the Earth spins, it generates a magnetic field. I'm being very cavalier with my physics here, I appreciate. And the magnetic field and the charged particles coming off the sun interact with the Earth's magnetic field as well, and we call that space weather. And it is very important because if the sun decides to get a little excitable, all of a sudden our GPS doesn't work, and sometimes if you have a huge space weather event, it might even knock out the power grid because it turns out power lines are antennae. And so there's a lot of, so there's a huge interest in understanding how the sun and the solar wind interacts with the Earth's magnetic fields and the magnetosphere, and also with the rest of the solar system. And this is a really complicated physical regime because it deals with plasma physics and it deals with large physical scales. But plasma physics itself is quite varied and complex, and you have to choose your plasma, the approximation that you're going to make, whether you're going to treat that plasma as a fluid or treat it as individual particles or both. Depending on the particular problem that you want to solve. It is almost invariably incredibly computationally expensive no matter which way you're going to do that. And one of the most important things about blue waters with regards to this is the size of the machine and the memory of the machine. And what it does is it allows you to go from two-dimensional simulations of these various phenomena to 3D. And when you go to 3D and when you go to the large dynamical ranges, what you find are a lot of phenomena become understandable that weren't before and that didn't manifest in 2 dimensions because of turbulence, usually. Okay, so the few results that I want to highlight. First off, the other thing that you get with blue waters, we have a machine with that capability, is people can write codes that do really complex and fascinating things. And so, Gaber Toth and Ward Manchester and their group at the University of Michigan put together a code that includes magnetohydrodynamics and particle and cell electrodynamics, so it treats plasma as both a fluid and a particle in different places. And this was the first 3D global study of the solar wind interacting with the Earth's magnetosphere using both this MHD approximation and the kinetic approximation, so the particle-based approximation. And this leads to some really interesting advances in our understanding of how these behaviors work. Another result I was fascinated to learn about was this work done by Reuterstein and collaborators, where they were looking at how turbulence, so all of this plasma is very turbulent. And the reason why is that there's basically no viscosity. So if you put your finger in a jar of honey, which I don't know why you do that, but if you did, you would stir it, and you don't get any turbulence. If you put your hand in a jar of water, in a bathtub, and stir it around, you can see little whirls and eddies. That's because it's less viscous. Plasma in this regime has zero viscosity, effectively. And so you get turbulence, and you get turbulence over huge ranges of physical scales. And understanding why when you put that turbulence in and stir everything around, where the energy goes, is a very difficult challenge. And this spectral plasma solver does a really fantastic job of, I believe, doing a 6-dimensional phase space simulation of how this plasma turbulence evolves over a wide range of physical spatial scales and temporal scales. And I was really astonished to read about that. Also, Nick Pogorelev, I just totally botched that, sorry, and his graduate student did some really wonderful global simulations of the interaction of the solar wind with the interstellar medium. And this is quite interesting too, because the Voyager spacecrafts, so Voyager 1 and Voyager 2, which have been sailing out of the solar system for about the last 40 years, have instruments in them that can measure the interaction of the solar wind with the interstellar medium. So the solar wind blows outwards and keeps the interstellar medium at bay, and our solar system is also moving through the interstellar medium. And so this, what's called the heliopause, moves back and forth depending on how active the sun is and sort of the local interstellar medium conditions. And trying to understand the readings from the Voyager spacecrafts has been quite a challenge. And the work that Nick and his student did has been really remarkable in terms of making sense of that. And then also, there's been some really wonderful 3-dimensional PIC simulations. So PIC is particle in cell electrodynamics, where you're treating that plasma as actual charged particles that you move around, and understanding phenomena such as magnetic reconnection, which is when two magnetic field lines where the magnetic fields are going in opposite directions bump into each other, and then instead of sort of carrying on in their merry ways, they connect. One goes up, one goes down, and you turn a lot of magnetic energy into kinetic energy, so it's a good way to move energy around. And that's a very hard physical phenomenon to model, and Liu and his collaborators have done that in 3 dimensions on blue waters. And again, the main thing that blue waters has brought to this regime is the ability to go to 3 dimensions from 2D and to do larger physical volumes like these global simulations that I mentioned, and also sort of combining different kinds of simulations together to understand these phenomena over a large scale. Okay, so I'm going to show a few movies. So this one is from Nick, and this is a movie of the interaction between the solar wind and the local interstellar medium. So you can probably figure out that the solar system is, well, technically the interstellar medium is going this way in the frame of the solar system, and what we're looking at is the colors are the magnetic fields. And so this is the distribution of magnetic fields. You can see where the interface between the solar system is. The physical scale is about, 400 astronomical units, which is 400 times the distance between the Earth and the Sun. So this is pretty big by the standards of people in this room, but very small by the standards of the universe, but bigger than the solar system. All the planets would fit inside the blue area. And what you're seeing is all sorts of really cool Rayleigh-Taylor instabilities that are happening because of the charge exchange between the ions and the neutral atoms. You're also seeing what are called tearing mode instabilities because of that phenomena called magnetic reconnection. And this is a really complex and interesting behavior that just would not have been explorable otherwise. This is a movie that was done by the Advanced Viz Lab of Homo Karamabadi's and Reicherstein's work. And this is one of my absolute favorite visualizations that has come out of blue waters. It was on I think a Discovery Channel show, but basically what you're looking at is the solar wind interacting with the Earth's magnetic field, and the colors there are showing you sort of the complexity of the plasma behavior when the charged particles from the solar wind encounter the Earth's magnetosphere. And the detail is just unbelievable. It's really, really cool. Okay. So the next thing I want to do is move to a larger scale and talk about stellar evolution, or at least more distant scale. So when I talk about stellar evolution, I'm talking about the lives of stars. Mostly in this context, I'm talking about the deaths of stars. And so stellar evolution is one of the problems that people first tried to do on supercomputers. I read this wonderful book by George Dyson on the origins of computing called Turing's Cathedral. and he mentioned that among the 4 problems that people tried to solve on the first academic supercomputers were weather modeling and stellar evolution. And this was in the late 40s, early 50s. And so good thing we solved that. Anyway, turns out you make a bigger computer, we make a bigger problem. But stellar evolution is fundamentally a really complex challenge because there is a great deal of physics. You're dealing with gravity, general relativity often. You're dealing with fluid dynamics, magnetic fields, radiation. You're often dealing with a lot of very complex nuclear physics because you've probably all heard of neutrinos, which are famous for interacting with nothing. It turns out that in the cores of collapsing stars, neutrinos interact with everything and actually produce most of the pressure in the star. And so it's, as you might imagine, very complicated physics. And you often get very different results when you go from 1 dimension to 2 dimensions to 3 dimensions, essentially due to the extra dimensions opening up more opportunities for energy to move around. So there's a lot of work that I'm going to show you, but it's also worth noting that a ton of software development for next generation stellar evolution codes has really been facilitated by blue waters. Okay, so core collapse supernovae. That happens when a massive star burns through all the hydrogen in its core, and then it burns through all the helium and whatever else is around, burns up to iron, and then iron, unfortunately, when you make that into anything heavier, you have to put in energy as opposed to get out energy, so fusion stops working and the whole thing collapses, and then by some mechanism explodes. And so it turns out that fundamentally it's pretty hard to make the darn things explode. And so the simulations that we're doing here include all of the physics that people can think are important. So like I said, radiation and magnetic fields and relativity and so on. And basically what we seem to think is that when the star starts to collapse, gravity and neutrino emission from that central remnant are fighting it out to try to make the star explode. So the things that have come out of blue waters. 3D, we have had the chance now to explore the 3D morphology and behavior of this neutrino-driven wind that's coming off of the supernova, and also how that affects the massive stars. Some mechanisms for how magnetic field generation in those stars and jets that are driven by these rotating, compact, very dense objects can actually power extra energetic supernovae. And also understanding how resolution, sort of increasing the spatial resolution, fundamentally affects the interaction between gas that is trying to collapse to the center of the supernova and all of the neutrinos that are trying to fight their way back out. And so, okay, so a couple quick movies. So this is a volume rendering of a supernova explosion by Adam Burrows. This is the core of the star. We're looking at something that's maybe a couple hundred kilometers across, and the whole simulation takes a fraction of a second. And what we're basically looking at is a rotating star and the stuff that is trying to collapse down onto that central core of the star and fight its way back out. Okay, we're going to skip that movie because we're out of time, or we're not going to have enough time. So compact objects. So moving on, compact objects are things like black holes, white dwarfs, and neutron stars. These are the remnants of stellar evolution. After there's a supernova, or after something like our own sun sort of slowly peters out at the end of its lifetime, you're stuck with these things that are incredibly dense and incredibly small. And so a neutron star is something like 10 kilometers in radius, so about the size of, this town, and it has a mass that's typically 1.5 times the mass of our own sun. So it's very dense. It's basically nuclear density. Black holes are smaller and denser, and white dwarfs are somewhat bigger. But basically, these compact objects are very interesting physical phenomena because they're very hard to see, but they are extreme environments where lots of cool physics happens, and they tell us a lot about how stellar evolution behaves, and we can use them to find out some very interesting things about the universe. Okay, so some of the really interesting highlights that Blue Waters has helped with. Blue Waters contributed to LIGO's detection of a neutron star merger. So 2 of these neutron stars, these basically nuclear density objects, small but solar mass, merge together and through general relativity radiate away gravitational waves. And so the detection of gravitational waves from black holes won Kip Thorne and 2 of his colleagues the Nobel Prize in 2017. That was black holes. Neutron star mergers are expected to be somewhat harder to detect, but we found one last year, and blue waters helped do that. Also, people have used blue waters to generate lots of these gravitational merger, the gravitational waveforms. And this was something that I was really interested to read about because you need a waveform, you need to have some idea of what you're looking for when you go look at the LIGO data because it's an incredibly sensitive problem. And so doing that is a challenge. And then people have done other things with much more physics, trying to understand how general relativity and magnetic fields and fluid dynamics all interact. All right, so let's see. So let's go to black holes. So black holes accrete all sorts of things. So you think of black holes as being completely invisible, and if you just left the darn things alone, they would be, but things have a way of finding their way into black holes, and so you find black holes because they have accretion disks around them that are full of gas that are getting pulled in, and as the gas gets pulled into the black hole, it gets heated up and produces tremendous amounts of X-ray radiation, gamma ray radiation, and other sorts of things. And those tell you all sorts of things about the black hole's behavior. You can learn about its mass, you can learn about its spin, you can learn about how magnetic fields are generated. Two of the really cool results that I wanted to mention are simulations of two supermassive black holes, and we'll get to supermassive black holes in a second, with accretion disks and sort of the evolution of those and their emission, their radiative emission, so what we'd actually see. And then also simulations of accretion onto the black holes where the disk and the black hole's rotation are pointing in different directions. So, okay, so let me just show this movie. This is from Scott Noble, and these are simulations with general relativity and magnetohydrodynamics of two supermassive black holes, which are the two things right at the bottom there, that are shooting out magnetized jets, the two white things that are coming out of the top, and showing how these orbit each other, and they have their own accretion disks that are embedded in a more complicated thing, a larger accretion disk. And we do see phenomena like this in distant galaxies, and we want to understand what exactly that does. And then this movie, which is, there we go, is the one that I find completely enchanting, which is the optical emission from this. So this is, if you happen to see this edge on, this is what you would actually see. Again, if you were, if you had a really good telescope, or if you were close enough, you'd be dead, but still. Okay, and then the last stellar evolution thing I wanted to mention was some work that was done by Paul Woodward and his group. And this is actually pre-explosion simulations of stars. And so when we study stellar evolution during the main sequence, during sort of the bulk of the life of the star, we often use a one-dimensional spherical approximation due to the huge expense of all the physics and the long lifetimes and so on. But there are moments in the star's evolution, like the one that's shown here, and I'll explain it in just a second, where all of the sudden, when you start burning a bunch of helium, or something happens, where suddenly that one-dimensional approximation, assuming the star is sort of sitting there hydrostatically behaving well, just completely breaks down. And what you have to do is go to three-dimensional simulations, like what Paul did here, to understand this. And so this is a model. What we're looking at is, I think it's the fraction of hydrogen around the center of the star, and you're looking at how convection is bringing hydrogen down to the center of the star so that it can be burned, and so that it fundamentally changes the evolution of the star. And what we can do is take three-dimensional simulations like Paul's, feed them back into these 1D simulations, which are 6 or so orders of magnitude cheaper to run, and make them much more accurate. Also, as a side note, Paul, every time I see these visualizations, it makes me think of impressionist paintings, and I think Monet would be proud. So, it's right up there with Starry Night in my vision. Okay, so last couple things. Galaxy formation. I have, about 3 minutes left? Okay. So supermassive black holes. I briefly mentioned that with Scott Noble's results, but every massive galaxy has a supermassive black hole in it. These are millions to billions of times the mass of our own sun, and they are lurking in the center of all of these massive galaxies. And interestingly, the mass of the black hole is tied to the properties of the galaxy that it sits in. And that tells us that there's some fundamental relationship between these black holes, which are very small, they're smaller than the solar system, and the galaxy, which is many orders of magnitude larger. And so we really want to understand why that is. Also, a further challenge is that there are really large supermassive black holes very early in the universe, so billions of solar masses, a billion years after the Big Bang. And that is really hard to explain in many ways because it's hard to understand how black holes grow that fast. And in the field of galaxy formation, this has been an area of very active research. So, Tiziana Di Matteo's group has shown that the most massive black holes in the universe grow in very compact spheroidal objects at high redshift in very rare environments. My own group, along with Mike Norman and John Wise, we've shown that stellar mass black holes, so things that come from the stars that I was showing you sort of one section back in this talk, are basically not going to be those supermassive black hole progenitors because they just can't grow fast enough. But when we do our simulations, we find plausible mechanisms for stars or for gas to collapse directly into thousands of solar mass black holes or tens of thousands of solar mass black holes, which lets you get around this growth problem. Also, Tom Quinn's group made some predictions for how supermassive black holes can get close to each other after galaxies have merged together, which will help them merge together and grow. And then finally, the FIRE collaboration has shown, using very sophisticated zoom-in simulations, how these supermassive black holes grow in the centers of galaxies by very sort of bursty accretion. I have barely any time to show a couple pictures, but this is from Tiziana. So this is a zoom-in of all of, so she did a simulation of a gigaparsec volume, so that's 3 billion light years on a side, give or take, of many, many galaxies using all of blue waters to try to understand, to try to find these rare supermassive black holes and see how they evolved. And zooming in, this is that galaxy that formed that enormous monster. Another one, this is my group taking a completely different tactic. Instead of huge volumes, we're simulating really small stuff to try to understand how average galaxies grow at that time. One of the most interesting outcomes that we had was that galaxies, when you look at these little guys in the universe, they produce radiation and they actually quench each other. And so when you go off and look at what's called the luminosity function, sort of galaxy distribution by brightness, you find that they're really, really suppressed at the low end because these galaxies are all essentially committing fratricide. And so finally, I'm going to skip down to the absolute last thing. This is another great example of something that you can do with blue waters. And so this is work that was done by Irina Butsky, who is a Blue Waters graduate fellow. And so these are simulations of individual idealized galactic disks where she's put in a ton of interesting plasma physics having to do with cosmic rays and magnetic fields and explored the different ways that those can drive winds out of galaxies and help them regulate their environments. Okay. I am going to wrap up now before I get kicked off of the stage. So just a few concluding thoughts. First off, thank you again to everybody who contributed their time to this and to the Blue Water staff for their support over the past 5 years. You know, the key things I want you to take away, astronomical and space sciences are fields where we rely on large-scale and high-performance computing to make any progress whatsoever. Blue Waters, as a machine, has been just a unique and indispensable resource for our community for the past 5 years. Blue Waters has really been a tremendous engine for scientific progress in our field, and that's something that really needs to be acknowledged. And we have made fundamental advances at all scales, from the Earth's magnetosphere to the formation of planets in the solar system, to neutron stars, to all the way to galaxies at the edge of the universe. And it's been really wonderful to be part of that. Thank you very much.
So we have time for a question or two while we're switching laptops. And anybody have a question? As a matter of fact, I'll ask for help from Jim to do the microphone for questions while we switch.
Anyone?
Oh, okay. Wow. Stunned silence. That's always what you want.
I found a new definition of very small. Now means smaller than the solar system.
Yes.
So
well, if you
Romy's going to be talking about very, 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 very small.
That's right. Though it's worth noting, if you do cosmology, big is really important, and then very, very small is very important. So, everything in between is, who cares?
Here we go.
Mark Neubauer, University of Illinois. So with the supernova story, I was wondering, my understanding is that now we're able to get supernovas to explode, and the critical role of the neutrinos is important, right?
That's right.
And so these are, I was just wondering, what do you think has to go in more, in what way do the models need to be more sophisticated? I mean, for example, to going forward, so I'm just trying to think of the complexity required to make more realistic supernova simulations. So like, for example, I can imagine the neutrinos are massless, but we know neutrinos are massive in mix. Actually, the mixing is probably important in this. So I was just wondering where you think the supernova program might be going in terms of the computational complexity of the models.
Right.
Is there a lot more to do, or are we kind of there?
So there's about 6 or 8 people in this audience who are really to be pissed off no matter what I say. However, I think it's reasonable to say that there are 2 really important pieces of this. One is doing simulations in 3D at high physical resolution, because turbulence, so when you have a neutron star sitting in the middle of your collapsing object with solar masses of material raining down on top of it, the interface between essentially the surface of the neutron star and all this stuff that's supersonically falling down on top of it is turbulent. And there's the density varies tremendously from place to place, and understanding how energy moves around in that, which is fundamentally a question of not just turbulence, but magnetized turbulence, which is worse or harder. You need spatial resolution to do that, and that fundamentally becomes a computational problem. And then the other important thing is essentially the nuclear physics, because as you rightly pointed out, you need to be able to model neutrinos and the interaction between neutrinos and extremely dense atomic matter. I mean, we're talking about an object that is essentially the density of the nucleus of an atom, but solar masses of it, a solar mass of it. And that is physics that needs to be constrained both theoretically, so through essentially nuclear physics modeling of nuclei and neutron stars, so like crystals and neutron stars and so on, but also modeling that interaction between the neutrinos, which can flavor mix and do all sorts of things. And that is at the very edge of what we can do with theoretical nuclear physics and also experimental nuclear physics. And all of that physics needs to go into the supernova calculations. And so you need to worry about the neutrino transport, the different flavors of neutrinos, and you also have to have a very good model of the interaction between the neutrinos and the baryonic matter and how that affects the equation of state. And so, so it's a combination of resolution and very careful microphysics. And I have clearly run out of time, so thank you all so much.